In this tutorial, we're going to go over practice questions in thermochemistry, chemical kinetics, electrochemistry, and also equilibrium. And so we are going to start with F5, which is talking about the effect of pressure on concentration. Alright, so now, or just the effect of pressure on solubility, let me say. A bottled soft drink contains carbon dioxide gas at a pressure of 5 bar over the liquid. So we have got a bottle, let's put it like that, and it has been closed. There is a liquid inside there, but on top of the liquid we have got 5 bar of carbon dioxide. Okay, and after opening, the partial pressure drops to 4.0 times 10 to the power negative 4. So that becomes the new partial pressure. And what we need to understand is when we open the bottle, when we open this, the pressure of carbon dioxide inside is supposed to balance with the pressure of carbon dioxide in the atmosphere so that they reach equilibrium. And so for it to become this, that means this is the pressure of the environment or the atmosphere. That is the one which it is going to reach equilibrium at. So the pressure of the atmosphere is 4.0 times 10 to the power negative 4, because that is the pressure at which it reached what? Equilibrium when you opened the bottle. Okay, now I want to calculate the equilibrium concentration of carbon dioxide in the soft drink before and after the bottle is opened. So before opening the bottle, according to Henry's law, concentration is proportional to pressure, that is Kp. So we are going to talk about first before opening the bottle. Concentration is going to be K, which is the Henry's constant, is been given as 3.1 times 10 to the power negative 2 more per liter bar, and we're multiplying this with the concentration of carbon dioxide before opening, so that is just times 5. So that would be 3.1 to the power times 10 to the power negative 2 multiplied by 5. So I always advise you to also punch on the calculator. So this bar and this bar is going to cancel out, and what I'm finding is 0.155, and the unit is going to remain more per liter. So this is going to be the concentration when the bottle has been opened, before being opened, and now after being opened the concentration becomes this. That means the concentration has reached equilibrium with the environment. Now the concentration is going to become Kp, and here K is same 3.1 times 10 to the power negative 2 more per liter bar. Now the pressure becomes 4.0 times 10 to the power negative 4 bar after the bottle has been opened. Same bar cancels out. So this will be, this is 3.1 times 10 to the power negative 2 multiplied by 4.0 times 10 to the power negative 4. So that is giving me a value of 1.24 times 10 to the power negative 5. The unit is more per liter. Okay, that becomes it. Now let's consider question A6 here. Yes, there's a question. Mm. Okay. Yeah, you have to present according to the number of significant figures. For example, concentration is Kp. For the second one, we've multiplied 4.0 times 10 to the power negative 4 by 3.1 times 10 to the power negative 3, and the answer that we have found is 1.24 times 10 to the power negative 3. So consider when you're multiplying, you consider the lowest number of significant figures. So I've got two significant figures here, two significant figures here. So give your answer to two significant figures. This is just 1.2 times 10 to the power negative 5 more per liter. Okay, that is it. Now question A6 here. Hmm. Okay, when you open the bottle, pressure always has to, because the pressure inside the bottle is always kept higher than the pressure in the environment when you are making a carbonated drink. So every time you open this bottle, that is the more reason you even hear a fizzing sound. That is because the carbon dioxide is going to move from the bottle into the atmosphere to reach equilibrium. The reason as to why it is moving out, because the concentration here is higher than the concentration in the what? In the atmosphere. Okay. So that is the more reason. Because concentration, you define diffusion as the movement of what? Substances from a region of higher concentration to a region of lower concentration. So that is what is going to happen. It will always move out of the bottle in order to reach equilibrium with the environment. Okay. Now question A6. When a 6.50 gram sample of solid sodium hydroxide dissolves in 100 grams of water in a coffee to cup calorimeter, the temperature rises from 21.6 degrees Celsius to 37.8 degrees Celsius. Calculate the enthalpy change in kilojoules per mole sodium hydroxide for the solution process. Assume the specific heat capacity of the solution is 4.18 joule per gram Kelvin. What is happening here is you get sodium hydroxide. You put this in a solution. What is going to happen is this is going to disassociate the sodium hydroxide into sodium plus and what? Hydroxide minus. Okay, let me change first the color. Alright, so that is what is going to happen. Now, when this disassociation happens, this reaction is going to lose heat. And the same heat which this reaction is going to lose is the same heat which the solution, what you've dissolved it into, is going to gain. And in this case, we are talking about the solution being made up of water. So that will be the solution, water. Okay. Now, according to conservation of energy, energy is not lost, it's not created, it's just transferred from one form to another. Now, in this case, the heat of the reaction here, the heat which the reaction, in this case, what when we talk about the reaction, we are talking about the decomposition of sodium hydroxide. When you dissolve it, it is going to release heat, and this is going to be equal to the same heat which the solution is going to what? Gain. So for the reaction, we are just putting a negative there, and then for the solution, positive, because the temperature of the solution did what? It increased. That means the solution gained heat. But where did it gain the heat from? It is from the same reaction which is happening. But how do you calculate the heat of the solution? So the heat of the solution is given by mc delta T. And the mass of the solution in this case is just the mass of water. They've given us what? 100 grams of water. Specific heat capacity of the solution is simply specific heat capacity for water, which is 4.18, which is joule per gram Kelvin. Then multiplied by the change in temperature. The final temperature, 37.8 minus the initial, which is what? 21.6. Well, even if this value is in degrees Celsius, but if we find the change, even if we convert this to kelvins, we subtract those values, it will be the same change as when we just use degrees. So I can just put Kelvin here for the sake of cancelling out units. Kelvin cancels. Gram and gram also does cancel. Now let's go on and just punch this. Okay, this is equated to negative Q. Yeah, it's negative, equated to negative Q of reaction. So we are saying 100 multiplied by 4.18 multiplied by what? 37.8 minus 21.6. And this value is going to give us, so negative Q of the reaction is giving us 6771.6. The value is going to mean in what? Joules. Okay, that is it. So we have found the heat of the reaction. This is the heat which the reaction is going to release. Now if we want to just have heat of the reaction, we're going to take the negative the other side, or divide everything by negative. So that will be heat of reaction is equal to, yes?
I have a question. In this question, since we've been given the grams of the sample of the solid,
Yes, so we are going to use that value. negative 6771.6 joules. Now remember, we want to give the answers in kilojoules per mole of what? Sodium hydroxide. But where does the per mole come from? Remember, the sodium hydroxide is the one which did release this heat. We want to give it in kilojoules per mole. So we need to determine the moles of sodium hydroxide. So first, the molar mass for sodium hydroxide. Hydrogen, let's use 1. Oxygen, this is 16.
16,
Sodium,
23.
23. So this will give us 24 plus 16. Of course, the periodic table which we are given is the one which we are supposed to use. This will be 40 grams per mole. So these are the number of moles. So remember, we want our value to be in kilojoules per mole. So what I'm going to say is heat is equal to, I'll just divide the same value, negative 677.6 joules, divided by the number of moles to convert it to joules per mole. So I'll divide by 40 moles. So this, we will see that the range is going to be in joules per mole, but we want it in kilojoules per mole. So I'll again multiply this. We know that in 1000 joules, 1000 joules is there for every 1 kilojoule. Why have I put 1000 joule down? Because I want a joule to cancel out with a joule there. So let's get to multiply this. So negative 6, I've even left out a 1 here. Negative 6771.6 divided by 40. And then that value we found also divided by 1000. So that will give us 0.16929. It will now be in kilojoules per mole. But of course, we know that the heat of the reaction is equal to the change in enthalpy at constant pressure. So Q is equal to delta H. And so delta H is going to become, we can give our answer to, how many significant figures are we even working with? So we can see we had 4 significant figures, 3 significant figures. So the lowest number of significant figures is 3. So this can be 0.169, and it will be in kilojoules per mole. So that is going to be the value for this one. Is it okay? All right. So let's proceed to question 7. Now question 7. They've told us that the composition of 0.5 molar hydrogen peroxide, that is H2O2, when this decomposes to hydrogen and oxygen gas, so H2 plus O2. This is a gas, this is a gas, and also this is a gas. Okay. As a rate constant, so they've given us the value for K, that is the rate constant, which is given as 1.925 multiplied by 10 to the power negative 3 per minute at that temperature. Now determine the time it will take for 80% of the original concentration of hydrogen peroxide to be decomposed. You want 80% to be decomposed. So if 80% is decomposed, how much percentage remains?
20.
So 20% has remained. Okay, 20% has remained, but we know the concentration of which was there initially. So if 20% has remained and it is 20% of the initial, how much has remained? So we're going to say what is remaining is simply 20%, which is 20 out of 100 of what was there present initially, which is 0.500, and this will give us 20 divided by 100, and then multiply that by 0.5, which is just 0.100 molar. Now we need to use the integrated rate law here, just by looking at the unit of the rate constant which has been given, per minute. This tells us that this is a first order reaction. And how do you get to determine the order? Unit of the rate constant, unit, is given as molarity to the power 1 minus n, and then time to the power negative 1. And this should be equal to, we've seen the unit which we've been given. We've been just given minute to the power negative 1. Where is molarity here? That means molarity is raised to the power what? 0. Time is always raised to the power negative 1. So here I've just written time because it can be in minutes, seconds, or what, but here it's already given in minutes. So this should tell us that the exponent for molarity should also be equal. 1 minus n should be equal to 0. So if we take n this side, we are going to see that n is equal to what? 1. This is the first order reaction. And from a first order reaction, what is the integrated rate law for a first order reaction? And that we need to know it. So the integrated rate law for a first order reaction, well, starting with a zero order reaction, that is simply a concentration of A at a certain time t is equal to negative Kt plus the initial concentration of what? A. But for a first order reaction, we are going to put natural log. So natural log at the very beginning there, and then natural log also here. Now, the initial the concentration at a certain time t, this is the final concentration. In other words, that is what we are saying. And the final concentration we already know, that is the 0.1, which is going to remain. So we want 0.1 molar to remain, and then negative K, that is the rate constant, we've been given as 1.925 multiplied by 10 to the power negative 3, but we don't know the time t. I've even left out natural log this side, and then plus natural log. What is the initial concentration? It's 0.5. We can see it, right? So this value, which is negative, I'm going to take it this side, and then this value I'm also going to take it this side. So this becomes positive 1.925 multiplied by 10 to the power negative 3t, and that is going to be equal to natural log of 0.5. And then this value, when it crosses the other side, becomes negative natural log of 0.1. And we know that when we have got logs which are subtracting, we can divide the terms. That is from the rule of logarithms. So this is 1.925 times 10 to the power negative 3t, and that is equal to natural log of 0.5 divided by 0.1. That is going to be it. Okay. 0.5 over 0.1, that is just a 5. And then natural log of a 5. Okay, so this will give us about 1.925 times 10 to the power negative 3t being equal to 1.6094. We can end here. We can continue writing. So time is going to give us, we are going to divide both sides by this value. So what I'm doing is 1.6094 divided by, that is 1.925 times 10 to the power negative 3. So that is giving us 836.0716428, which we can just write as, what are the number of significant figures we are dealing with? Okay, here we have got 3 significant figures, 3 significant figures. Here we have 4, so the lowest is 3. So you can give it to 3 significant figures as 836. But this, we are dealing with what? What is the unit of time? It's in minutes. So that is going to be it for this one. Alright. Let's see if we have got another question on this paper. Okay, that is going to be all for this one. We'll see you in the next video. I will continue going over other questions.